Okay, so let's talk about one more type of complicated research designs. And these designs broadly are known as time series designs because the variable of time is an important factor for some issues. In some designs, simply the mere passage of time might be an important variable, but in other designs, there's some treatment that's made in between some observation at point A and at point B, and we want to see if there's some effect of that treatment. Earlier in class, we talked about a researcher who might be interested in reducing school bullying, and they might randomly sample a number of schools and then randomly assign one group of schools to receive some bullying treatment, and then the other schools are going to receive some control group. So that's a time series design. So let's talk about a few different types of time series designs. But before we get started with the time series designs, I want to bring up one idea that we haven't talked about yet. So imagine that we have some test, and we're going to give it at time A. So test at time A, and we're also going to give the test at time B. So we have the same test, and we're giving the same test at 2 times. Now, people's scores or the subject scores, they might be schools or automobiles or whatever, they could change from time A to time B. If we have a test that's measuring something that shouldn't be changing from time A to time B, then those scores on the tests should be roughly the same, right? They're not going to be exactly the same because of the variability inherent in almost everything in life. So there's going to be some variability, but what we should see is that individuals who score high on an IQ test at time A should score high on an IQ test at time B, especially if that's the same test. So the ability of a test to give you the same values each time that it's given is reliability. Now this is completely different from validity. You can have a test that's completely reliable and completely invalid. You can have a test that's completely reliable and completely valid, or you can have a test that's valid but unreliable. So let's imagine a situation. I get on my scale in the morning and I look down and it says 170 pounds. That's one observation. I get off the scale, I jump back on, it says 170 pounds. This is actually measuring my weight properly, right? If I were to pick up a laundry basket, my weight would increase. If I were to take off my clothes, my weight would decrease, right? So that scale is validly measuring my weight. It's also pretty reliable. I got on, it was 170, I got off, I got back on, it was 170 again. Let's think about something else that's valid but a bit less reliable. So when I get sick, I like to take my temperature, and if I have one, I prefer using a glass thermometer with mercury inside. I like using these because they are both valid and very reliable. If I'm 98.6 right now, I shake it down, put it back in, I'll be 98.6 again. I've found it's possible that the technology has changed, but there are some of the fancy thermometers where you can rub it across your forehead or do some other things, stick it in your ear. I found that I can rub it across my forehead and it will read, let's say, 101.2, and I'm like, oh my goodness, I'm really hot, is that right? And I read it again and it's 100.8. So it's valid. The higher my temperature, the higher on average those readings are going to be, but it's not quite reliable, or as reliable, right? Because there's a lot more variability from one moment to the next. So something that would be incredibly reliable but not at all valid is if I were going to measure your IQ by your shoe size, right? So if you think about it, I measure your shoe size, it is what it is. I measure it again, it's the same thing, but really that doesn't have anything to do, or it shouldn't have much to do with your IQ, right? So there I would have an invalid measure that's completely reliable. Now the reason I bring this up is because if we're going to test at time A and time B, it would be useful if our test was reliable. So this is known as test-retest reliability. There are other types of reliability too. Imagine that we were doing a developmental research study where we were looking at interactions between the mother and child, and we were looking for positive, negative, and neutral interactions. We take a video of them interacting, and then I rate them. And I rate the number of positive interactions, neutral interactions, and negative interactions. But just relying on my ratings alone might not be the best idea. Maybe I'm not the best rater. So what we can do is get someone else who's also been trained to rate the videos for positive, negative, and neutral events, and have them rate the same videos. Now what should happen is that my ratings should line up with their ratings. In that case, we would have inter-rater or between-rater reliability. So reliability is different from validity, but it's also something important to consider in the context of research design. So, we've got our tests and we've got the times. Now imagine that we are interested in some intervention, and I'm just going to indicate the tests. So A, this is going to represent a baseline, not necessarily a time anymore. And B is going to represent the intervention, or the test during the intervention. And you can imagine that I give a test before the intervention and a test after the intervention. Now this is good. Maybe I'll see that after the intervention scores are higher or lower or faster or slower or whatever the dependent variable is. However, there's a problem. It's possible that the intervention, because the intervention was given at a particular point in time, the change in the scores during the intervention or after the intervention might not actually reflect the intervention, but they might reflect some change, some historical change in society. So you could imagine if I was going to do some gun safety program in some area, and at the same time that I do my gun safety manipulation, there's a change in the laws relating to open carry or anything else, and you find a change after my intervention, it's possible that that doesn't really reflect my intervention at all, and it instead reflects a change in the laws. So one thing that we can do is we can put another test, remove the intervention, right? So stop putting up my billboards or my radio ads or whatever my intervention is, and then look and see if things are staying the same, which would potentially indicate either a historical change at this point that carried over, or a long-lasting effect of my intervention. But if we notice that, let's say we're plotting performance, if we see performance do something like this, this would suggest that the intervention is really cool, because at the times that we measure without the intervention, we're observing the same type of data, and only with the intervention do we see the change. So that would allow us to make much stronger claims about the intervention as opposed to anything else really playing a major factor. So what if we aren't, if we see something like this, so the first test, then we have the intervention, and then we test again. If we see something like this, maybe we want to say, wow, look, our intervention was super powerful, it's awesome, people need to use this intervention if that's something that's producing socially desirable outcomes. But you have this problem about history, right? So at the time that you gave the intervention, something might have changed. So that's an issue. So how do we potentially avoid this problem of history? Well, the Solomon four-group design is going to take care of this issue and some other issues too. Let's start off with the first two of the Solomon four groups, because the first two are something that we've seen before. So O represents an observation, X indicates a treatment, or you can imagine experimental condition. So we have some situation where we have a test, some treatment, and then another test. And we compare this with a test, no treatment, and then another test. This is just like the bullying thing that we've talked about, right? So both schools get the pre-tests, One of the schools gets the intervention, the experimental intervention, and there's some other type of control for the other. And then finally, there's the post-tests. Now, what is this great for? Well, you can imagine if we were to plot performance for these things. Notice we just have 2 tests here, right? Just 2 tests. What we would hope is that for our experimental condition, we want to see some improvement, and I'm indicating improvement by going up. But improvement, if we're talking about less time, then that would actually go down. But that's really neither here or there, because the point I'm trying to make is to contrast this with the control. So what we would want to see is that the control at time A should be identical with the experimental condition, right? We've randomly assigned the different schools or the different participants, whatever they are, to these different conditions. So these should be identical at time A. So we would want to see something like this for time A. Now, hopefully, what we see is that we have improvements with our treatment and no improvement with our control. Or maybe we have some improvement, but we would want to demonstrate that our treatment is better than the control, right? So this is control. What we would not want to find would be something like this, where the 2 basically overlap each other exactly. If you found something like that, that would suggest that something at this point in time, I'm going to say history, something at this point in time besides the treatment actually affected things. Now, one of the problems with this type of design is that because we have pre-tests for both of these conditions, it's possible that any change we might see as that we think is related to the treatment might not necessarily be related to the treatment, or well, at least the treatment independently. And instead, it could reflect getting the treatment after a pre-test. So this has important implications. Think about it. If you're doing research, you might want to show that the schools actually changed, right? Because without that pretest, if you showed a difference between the experimental and control, there's always the possibility of a confound, even if you have used random assignment, which will reduce that possibility. That possibility is still there. So by giving the pretest, you're able to make stronger claims about changes. However, it's possible that this only worked because of the pretest. And you've got no way to really address that possibility with the current design. So let's think about potential variables here. We have variables of a pretest, we have we have a variable of treatment, and we have our dependent variable, which is the post-test, right? So we're going to leave the post-test alone. That's going to stay the same. So it says 4 groups, so let's just put things up here. Treatment, we can either have it or we don't have it. Pretest, we can either have it or don't have it. So if you think about some of the other designs that we talked about, visual search, we could have set size 6 or set size 12, and we also could have a conjunction search or feature search. So we had 2 variables, 2 levels, we could cross them and come up with 4 total conditions. Same thing here, treatment. We can either have the treatment or not have the treatment. Pretest, we could either have the pretest or not have the pretest. So you can imagine that the other 2 groups would be something like this. So here, not only can you see if there are any effects, let me indicate 1, 2, 3, 4, these are different groups. Not only can you see if there are any effects of history, but you can also see if the pretesting is important. So let me just contrast these 2 groups right here. So 1 and 3. So 1, I have a pretest and a post-test. What I would want to see is that 3 also, let me use a different color, 3 should also be right there on top. If it's just my treatment that's working. If we see something different, if we see this down here, well, since this test is basically the same as that test in terms of which test that they got, if we see that their performance here even after they got the treatment, is like the performance here before they received the treatment, then that suggests that you just have a testing effect and that the treatment really didn't matter at all. So by using these 4 different conditions, you can answer different questions about history, about the importance of pre-testing, and things of that nature. The final type of design that I want to mention is really important if you're doing some type of intervention that is going to really help out participants. Imagine that you're doing some treatment on depression and you want to alleviate depressive symptoms and you want to help people feel a lot better. Imagine that you did something like this, right? You've got 2 groups, maybe you do the whole 4-group design, and you see that these groups of individuals both do better after they receive the treatment. Well, from an ethical standpoint, if you know that that treatment is working and you are working with these participants, it would be unethical to withhold a treatment that works from your participants. Also, it would be really important to replicate the study that you have, right? Replication is important. Maybe things were just a fluke. So the final type of design is going to be able to address issues like that. So here we have one group. We have a pretest. The other group also has a pretest. Then we have some intervention, and both receive, I'll call this a post-test, or maybe an intermediate test. There's this intermediate test here. And we would want to see that this group is doing better after the intervention than this group is, right? Now, if it's really our intervention that worked, what should happen? Well, if we give this group the intervention here, they should perform better there. We can also figure out how strong our intervention is. So imagine the situation. We're going to have 3 data points for each line. This will be my blue group. And this will be my red group. So what we would want to see is that the baseline, right? These should be baseline. There's been no treatment. These should stay constant from time A to time B. And then after the intervention, this should hopefully go up. Now, with the blue group, if our random assignment was successful, the data point for that first observation should be identical between these groups. But we treat them. So at time B, we would hope that they would be doing better. Now, if our treatment doesn't have long-lasting effects, you can imagine something like giving somebody blood pressure medication. If they stop taking the blood pressure medication, what's going to happen? They're going to go back down, right? So if you saw something like this, you would know that you had an effective treatment, but you would also know that its effects aren't particularly long-lasting. If, however, you were to observe something like this, that would indicate that the treatment worked. Notice when we gave a treatment here, the test afterwards improved. Same thing here, the test afterwards improved. But since we also have this additional delay, we can see that that improvement carried forward in time, which is really important to know. Also, this study replicates itself, right? We had one observation where the treatment improved things, and another observation where the treatment didn't improve things. You can imagine that if you really wanted to, you could do something like the Solomon 4-group design and get rid of these initial assessments for other groups. So you could have something like up and right. And if you really wanted to go crazy, you could do the same thing and get rid of that middle test as well and see if there are any effects of the different levels of testing. Okay, so we have covered everything that I wanted to cover this semester in terms of research methods design. Congratulations, you've made it through. We're going to be talking about ethics after that, and hopefully we'll have some fun. Bye.